Integer overflows and underflows. Introduction. What is integer overflow and underflows? Well, whenever assigned and unsigned integers have exceed their positive and negative value ranges due to acid math, we say that an integer underflow or overflow has occurred. As a quick reminder, signed numbers represent negative numbers via 2's complement. 2's complement essentially involves flipping all the bits and incrementing by 1. C signed types break up the bit range into half signed versus unsigned values. Consider the following for 8-bit numbers. The unsigned range goes from 0 to 255 or 0 hex 0 to hex FF. For signed numbers, this range goes from 0 to 127 and then from negative 128 to negative 1. Pay attention to the signed bits. If the most significant bit is 1 for a signed integer, then this is a negative value. Otherwise, it's either 0 or a positive value. Likewise, for 32-bit numbers, the unsigned range goes from 0 to 4 billion and the signed range goes from 0 to 2 billion and negative 2 billion to negative 1. Acid math is bad and leads to acid bath. Every time we have an attacker-controlled input data as an operand for arithmetic operations plus, minus, multiplications, or shifts, we are likely to have an acid bath, which as we know is detrimental to existence. Let's discuss integer overflows. Well, starting with unsigned overflow. In unsigned integers, there is no representation for negative numbers. So you can only go from 0 to the max integer number, and if you increment it any additional time, then you would wrap around back to 0. And this can be illustrated in this animation. Suppose that we have an infinite loop that increments I starting from 0, I goes to 1, then I goes to 2, then assuming that I is all the way at 254, one more increment, I is at 255. If we increment it another time, I is going to cross the unsigned boundary and go back to 0, and we will say that an integer overflow has occurred. For signed overflow, starting at 0, if we increment I, go all the way to 127. If we increment I one more time, I crosses the boundary to the least negative value for signed single byte integers, and now we have negative 128, and an integer overflow is said to have occurred. Subsequently, if we continue to in fact increment I down the negative value ranges and we are at negative 1, if we further increment I again, I crosses the boundary one more time, and now I's value is 0 and an integer overflow is said to have occurred again. We can see here underallocation and overcopies are known consequences of integer overflow. And as this slide illustrates, we want to listen to your teacher and look at the pictures. Now, assuming that we have a big number that is attacker controlled, so that's the stuff that's highlighted in red. When we carry out this arithmetic operation for addition with a constant, if the number is big enough, that is, if the number is close to the boundary, then this would cause a wraparound and yield a much smaller number. Now, if we allocate with that much smaller size, then what we would have is an underallocation. Likewise, if we have two sufficiently large integers, when added together, would yield to an integer overflow, and then the resulting value would be much smaller than intended and would have once again an underallocation. Likewise, if we have a sufficiently large number that has been multiplied with a constant, we could also have an underallocation. If any of these sufficiently large numbers are specified as a size to a memcopy operation whose destination was allocated using those problematic arithmetic operations, then we can see how an overcopy would in fact occur. Now let's look at this trivial example. Pay attention to header. It is a struct that just contains two unsigned long values, magic, which is hard-coded, and size, that is specified by the user. If the user then specifies an arbitrarily large integer close to the unsigned long boundary, then we can say that header size contains that very large number, and when using subsequent calculations to determine allocation size would yield to integer overflow. The consequence of allocation size being smaller than intended would cause an allocation to be made that is smaller than intended, which would be an under allocation. Any subsequent operations on this buffer that are copy operations would actually potentially lead to a heap buffer overflow. Now, although we do say or illustrate here that this code is safe, it could actually be another instance of heap buffer overflow if the buffer created by the malloc sign was actually too small for even the header to be written to it. But I want to draw your attention to the further mem copy operation that takes place when header size, which is the arbitrarily large size specified by the user, is used to determine the size of data that's written into the buffer. At this point, an overcopy is going to occur because ACID size and source is being copied into an ACID underallocated buffer. The result? Well, let's take some examples. Assuming that we specify the self-reported size of 1 and the string what up, the allocation size value would be hex 9 because the size of the header would be 8 plus 1, that gives us 9, but then the only data being copied is of size 1 byte, so that would just be for the character W. Subsequently, if we provide hex 10 as the size and the string what up, then the allocation size would be hex 18 and the entire string will be copied into the buffer. The situation gets interesting though when we specify something such as hex FFFFF, because then the allocation size would be a result of an integer overflow x7, and then whilst copying that string what up, which is more than the allocation, we would experience a segmentation fault. The prior code actually contains other opportunities for crashes, which are not particularly what we care about in this section. Specifically, if we yield an allocation size such that we copy more than the data that has been provided, then an access violation error will occur, and that would also lead to segmentation fault. Integer overflows may also occur below the surface in your allocation code, in allocation libraries. This was observed by Microsoft Azure IoT folks who had done a bunch of analysis of IoT libraries and discovered a grouping of vulnerabilities they termed bad alloc. What typically happened was that the actual code reading for calloc and malloc were vulnerable to integer overflow. This typically happened when you requested, say, X bytes, but then the library had to add an additional Y bytes for some sort of metadata. But then if X was close enough to the boundary, then an overflow would occur, which would lead to an underallocation. As illustrated earlier, let's see a normal malloc call that has to perform this kind of additional computation to determine the size of the allocation to be provided, because that allocation also contains metadata. In this case, if the size was 1024 and the additional data to be allocated was 8 bytes, then we get an allocation size of 1032. But if the actual input was the size 4 billion, which is close to the boundary, then adding an additional 8 would lead to an integer overflow and lead to an underallocation, acid bath. And likewise with calloc. This was an example from those same series of bad alloc vulnerabilities. In this case, X wanted size, if it was large enough and close to the boundary, when computed as follows with heap struct size, would yield to an integer overflow. Likewise, when performing the byte alignment. The following libraries were seen to be vulnerable to this bad alloc series of vulnerabilities. Whilst we're at it, we want to draw your attention to allocators that actually provide a valid allocation for size 0. Whenever you see this is bad code and would always lead to a heap overflow. For additional reasons on integer overflow, see the reference slides. Now let's talk about integer underflows. So in integer overflows, we tend to increment data or perform some sort of multiplication that leads to the integer value crossing a boundary. In integer underflow, what we actually have is decrementing of values close to a boundary that causes a wraparound. So assuming that we have an unsigned char value I starting at 0 and we decrement. For unsigned values, there is no concept of negative numbers. So when we go I minus 1, we go 255 and we say an integer underflow has occurred. Subsequently, if we continue to negate I through the entire range of possible values, again, an integer underflow has occurred. For the signed counterparts, the range is split into half. However, if you decrement 0 one more time, you get -1. You've just crossed the boundary, so we call that an integer overflow. Now let's observe signed underflow. Assuming I is still an unsigned character I, but then I would be interpreted as a signed value at some point, then when you decrement I, that representation of 255 actually is interpreted as -1, and we would say that an integer underflow has occurred. Subsequently, if we continue to decrement I past -128, we hit the highest possible value, 127, and an integer underflow has occurred once again. Back to our cartoon illustration, integer underflow leads to an underallocation and overcopy. So if an attacker is able to control the size of a memcopy operation such that the calculation of the size yields a negative number, which will be interpreted as an unsigned integer that is arbitrarily large, then an overcopy is going to occur. Now, let's go look at real examples.